So now we're going to move on to kind of what the bulk of the chapter is. The chapter is called Aromaticity. Okay? So what the heck do we mean by aromaticity? All right, and we're going to take our quintessential example of an aromatic compound, benzene, here. All right, so remember we talked about isolated dienes versus conjugated dienes. And when those dienes are conjugated, it provides this extra stability to this molecule, right? Well, now if we take a conjugated diene and we link it up into a ring, it's like conjugation on steroids. This thing is just super ridiculously stable, okay? So when we talk about an aromatic compound, they are way more stable than expected. Okay, but to be an aromatic compound, you can't just be a ring of double bonds. You actually got to meet two special criteria. So one, you are a fully conjugated ring. All right, and that checks out. Just a ring of a bunch of conjugated pi bonds. Okay, that's pretty expected, I think, right? I mean, you got to be a ring, you got to be all linked up. The second rule seems to come out of nowhere, and we'll talk about this a little bit more. But not only do you have to be a fully conjugated ring, you also have to have an odd number of pi bonds within that ring, of delocalized electron pairs within that ring. Okay, so let's just convince ourselves real quick that benzene is indeed an aromatic compound. Okay, remember what it meant to be fully conjugated is you had to have that perfect spacing of double bond, single bond, double bond, right? But the real reason that that was the case is because all of those carbons have to be sp2 hybridized. They have to have that p orbital where those electrons can freely move around. Right? So if we look, every carbon about our double bond, this carbon here, this carbon here, this one here, this one here, this one here, this one here, these are all sp2 hybridized. So we indeed have a fully conjugated ring. Right? Remember, this is important because we have these p orbitals, and the whole idea of conjugation is that the electrons are going to spread themselves out between all of these rings here, between all of those p orbitals, which I feel like just looks like a mess when I draw it, but hopefully you get what I'm saying here. One lazy man's way to draw benzene, and we don't actually use this much in organic chemistry, is to sort of do this dotted line in the middle to kind of show that those electrons aren't locked into place. Those pi bonds aren't locked into place. They're constantly moving all the way around that ring, right? Circling that ring constantly. They have spread themselves out to all possible positions. Okay, I will tell you, I hate this. Does not accurately account for how many electrons are in that molecule, so it drives me nuts. But you will see that. Okay? But again, then the weird thing is this second rule here. Our odd, whoops, that's not what I want. Our odd number of electron pairs. Let me go grab a good benzene. Okay? So let's just convince ourselves. We said that benzene was a fully conjugated ring. Got all of our sp2 carbons. So that's what we're going to be looking for when I say a fully conjugated ring. I guess let's just be clear. That means all sp2 hybridized atoms. But now we have to have an odd number of delocalized electron pairs here. Okay? So electron pairs we're counting. So each of these pi bonds that are delocalized counts as one electron pair. And we got 3 of them. So do we have an odd number of electron pairs? Cool. All right, so benzene meets this criteria here for being super stable aromatic. All right? Let's just use these rules for, we'll talk a little bit more about why there's this stability and why these rules exist, but let's make sure that we can apply these 2 rules to different molecules, okay? Polygon drawing is a little rough today, all right? Okay, so we said if it satisfies both of these rules, we consider that to be aromatic, right? So benzene, we gave that aromatic designation because it followed rule 1 and followed rule 2. All right, so let's go to this one right here, cyclopentadiene. Okay, do we have a fully conjugated ring? All right, let's see. This carbon right here that's attached to this pi bond, that's sp2. So are these attached to these pi bonds. All of these are sp2. What about this guy right here? That is not sp2 hybridized. There are 2 carbon bonds and 2 hydrogens on there. This would be sp3. So this thing right here breaks the conjugation in that ring. There is no p orbital for those electrons to freely move in a circle. So this one right here violates rule 1. don't get me wrong, these are conjugated pi bonds, but we do not have a fully conjugated ring, right? We don't have every member of that ring sp2 hybridized, okay? So although this is a conjugated pi bond, it does not satisfy rule 1. If it violates rule 1, we have a special name for these compounds. These are simply non-aromatic. All right? If it violates rule 1, I'm not even going to bother to go on to rule 2, right? I'm just going to throw it in that non-aromatic bucket. All right, let's look at this one here. This is a little scary because it's got this fused ring system. But we're just going to jump around and say, all right, is this one sp2 hybridized? Yes, because I got that pi bond. What about this one? And this one? And this one? All right, now these are the hard ones. What about this guy right here? Yes, it is also sp2 hybridized. There are only one, There are 1, 2, 3 bonding regions. There's no hydrogens on that carbon, right? So this is still sp2 hybridized. If I move around my ring here, all of these carbons are indeed sp2 hybridized. So now I'm going to move, so we check. We satisfy rule 1. Let's move on to rule 2 here. I'm going to count the number of delocalized electron pairs. Right? So these are these pi bonds. 1, 2, 3, 4, 5. Do I have 5? Yes, I do. Do I have an odd number of delocalized electron pairs? Yes. So satisfies rule 1, satisfies rule 2. So this would be an aromatic compound. Okay, because again, satisfies 1 and 2. All right, now let's move on to this wonky looking stop sign over here. Okay? Let's see if we have a fully conjugated ring. Are these all sp2 hybridized carbons? This one's about a double bond. This one is. So I go around my ring. Check. Okay? So this one satisfies rule 1. But now we're going to move on to rule 2 here. I'm going to count my number of electron pairs, my delocalized electron pairs, these pi bonds. So that's 1, 2, 3, 4. Does this one satisfy rule 2? No, I got an even number of electron pairs. So if it satisfies rule 1 but violates rule 2, we got a special name for these as well. These are what are called anti-aromatic compounds. All right, and we'll talk a little bit more about why this is next class period, but for right now, aromatic, good, super duper stable. Non-aromatic, meh, just a regular old conjugated diene. Anti-aromatic is bad. Anti-aromatic compounds are far less stable than you would predict based on just looking at this conjugated ring. You'd be like, oh, they're all conjugated, they're happy. No. We're going to see, for some reason, when you got that even number of electron pairs in there, it's terrible. It's way worse than you would expect it to be stability-wise. Okay? All right, so let's just do some more here. And I will say, I guess, let's take a step back. This is the name of the game here. You're going to be given a molecule, and you're going to classify it as being aromatic, non-aromatic, or anti-aromatic based on those two rules that we laid out, right? If it satisfies both rules, it's aromatic. If it violates rule 1, it's non-aromatic. You don't even move on to rule 2. But if it satisfies rule 1 but then violates rule 2, that's that super bad anti-aromatic. Okay, so actually let's do one more example together and then I'm going to let you loose on some on your own. Let's take this same cyclopentadiene. All right. Originally there were these 2 hydrogens on this carbon up here. I'm going to get a strong base and I'm going to deprotonate that carbon. So now what I have is a carbocation up here. Okay. Cool. So we're going to go and we're going to do our first rule. We're going to see if we have this fully conjugated ring. Okay. Hopefully we can all see that these are sp2 hybridized. All right. But now what about this carbocation here? An important thing to remember about carbocations is that they are carbons with 3 bonds and no lone pairs. So they have those 3 electron regions. They are indeed sp2 hybridized. Carbocations do indeed have a p orbital. It's just empty. All right? So carbocations, that's part of what makes them so great at accepting pairs of electrons from nucleophiles, is because they're sitting here with this empty p orbital ready to go, ready to accept a pair of electrons. So when you're going around your ring and you're asking yourselves, is this atom sp2 hybridized? Is this a fully conjugated ring? When you get to a carbocation, the answer is yes. Those carbocations are sp2 hybridized. Okay? The big difference is, unlike our sp2 hybridized carbons in the rest of the ring, that p orbital is sitting there empty. So they're not contributing any electrons to the ring here. They don't have any electrons that they're delocalizing, but they're just sitting there ready to go with an empty p orbital ready to accept electrons. Okay? So carbocations sp2 hybridized, but they have no delocalized electrons. Okay, so does this molecule right here satisfy or violate rule 1? Satisfies. Now we're going to move on to rule 2 here. I have 1, 2 pairs of delocalized electrons. And again, does this carbocation add anything? No, right? It's got an empty p orbital. So it's sitting there. It's got its hybridization ready to go, but it does not contribute any electrons to the ring. So this would be an anti-aromatic compound. Cool. All right. So with that in mind, let's do a few more examples here. Oh, sorry. I guess let me finish this one off. All right. All right, so again, classify these as aromatic, anti-aromatic, or non-aromatic. All right, cyclobutadiene. What do we get for this one? Do we have a fully conjugated ring? Yes, all of these are sp2 hybridized. Do we have an odd number of electron pairs? No, we got an even number. So this is anti-aromatic. What about this next one here? This 7-membered rings, 7-membered polygons. Biggest pain in the butt to draw here, all right? Do we have a fully conjugated ring? No. We have these all sp2 hybridized. We got these conjugated pi bonds here, but the ring is not fully conjugated. You have this one sp3 hybridized carbon up here messing everything up, okay? So those bonds can't talk to each other in that full ring. So I'm not even going to move on to step 2. This is just non-aromatic. And what about the next one here? All right, so do we have a fully conjugated ring? Again, we're going to go around the circle. Yep, double bond, double bond, double bond, double bond, double bond. And then I get to this carbocation. And I'm like, crap. Is this also sp2 hybridized? Yes, carbocations are sp2 hybridized. Cool. So my ring is fully conjugated. Those electrons can move in a circle. So now let's see if they're happy to do so. We need to figure out how many electron pairs we have. Right? So 1, 2, 3. And what about that positive charge? No, it's not bringing any extra electrons. It's just got that empty p orbital. So I do have my odd number of electron pairs. This would be an aromatic compound. Okay? Cool. So for right now, we've introduced this idea of aromaticity, and basically all we've said about it is that aromatic compounds are super stable, and they have to meet these 2 criteria here. They have to have a fully conjugated ring, but also this kind of odd one, where there has to be the odd number of electron pairs. Okay? If you meet both those criteria, you're aromatic. If you don't meet the first one, you're just non-aromatic, you're just conjugated double bonds. And then if you meet the first one but not the second one, you're this extra bad category called anti-aromatic. All right, so given the structure here, should be able to apply those rules to determine whether a compound is non-aromatic, aromatic, or anti-aromatic. Cool.